We think we know our solar system, the familiar planets, the blazing sun, the silent dance of moons and asteroids. But what if I told you that lurking just beyond our understanding are secrets so puzzling, even the brightest minds on Earth still can't explain them? Picture this, right now as you watch this, there are forces at work in our cosmic backyard that defy logic, phenomena that leave scientists scratching their heads, and mysteries so deep they could rewrite everything we thought we knew about space. This isn't science fiction, it's real, it's happening, and today we're diving headfirst into the 30 most mind-bending unsolved enigmas of our solar system. From the moment humans first looked up at the night sky, we've been driven by curiosity. But here's the wild part: the more we discover, the more we realize how much we don't know. Take Jupiter's great red spot, a storm so massive it could swallow Earth whole. Yet no one can explain why it's been raging for centuries or why it's slowly shrinking. Or Pluto, that tiny world at the edge of our cosmic neighborhood, hiding glaciers of solid nitrogen that somehow flow like water. And then there's the Moon, our closest companion, with its bizarre magnetic swirls that shouldn't exist. These aren't just quirks, they're cosmic riddles waiting to be solved. And each one holds clues to the untold story of our solar system's past, present, and future. So why does any of this matter? Because these mysteries aren't just about distant planets or abstract science, they're about us. Every unanswered question is a reminder that the universe is stranger, more dynamic, and more wondrous than we ever imagined. And as we explore these 30 puzzles together, you'll see how each one ties into the bigger picture. How planets form, how life might arise, and whether we're truly alone out here. This isn't just a tour of the unknown, it's an invitation to wonder, to question, and to feel that thrill of discovery alongside the astronomers racing to unravel these secrets. Ready to uncover what's hiding in plain sight? Let's begin. Between Mars and Jupiter, where you'd expect to find another planet, lies a chaotic jumble of space rocks, the asteroid belt. But what if that wasn't always the case? Centuries ago, astronomers noticed a bizarre gap in the solar system's lineup, a place where a world should be. Some scientists believe this region was once home to a full-fledged planet nicknamed Phaeton before something tore it apart. The clues are written in the asteroids themselves. A handful of these rocky fragments share strange chemical signatures like Ceres, with its eerie patches of bright salt deposits, or Vesta, whose surface hints at ancient lava flows. These aren't just random debris, they're pieces of a puzzle, remnants of a world that might have been smashed apart by a catastrophic collision or ripped to shreds by Jupiter's overwhelming gravity. But here's where it gets even stranger. If Phaeton did exist, where's the rest of it? The entire asteroid belt combined has less mass than our moon, hardly enough to account for a full planet. Some theories suggest most of Phaeton was flung into deep space or swallowed by the sun, leaving only these scattered fragments behind. Others argue it was never a planet at all, but a failed one, a world that never quite came together in the early chaos of the solar system. The truth we may never know for sure, yet every time a spacecraft visits the asteroid belt, like Dawn's mission to Ceres, we uncover new oddities like its mysterious glowing craters that keep the mystery alive. What makes this more than just cosmic archaeology is what it tells us about our own planet's past. If a world was destroyed here, it's a chilling reminder of how violent the early solar system was and how lucky Earth was to survive. Could Jupiter's gravity have shielded us by shredding Phaeton instead? Or did its destruction send shockwaves that shaped the orbits of other planets? Each rock in that belt holds a story, and solving this mystery could rewrite the history of our entire celestial neighborhood. One of the most violent cosmic events in recorded history left no trace of its origin, just a wilderness of flattened trees and a mystery that's lasted over a century. On the morning of June 30th, 1908, deep in the remote Siberian taiga near the Tunguska River, A fireball brighter than the sun tore across the sky before exploding with the force of 1,000 Hiroshima bombs. Witnesses described a column of blue light splitting the heavens, followed by a shockwave that knocked people off their feet hundreds of miles away. But when scientists finally reached the epicenter decades later, they found something baffling: no crater. Just 200 square kilometers of forest scorched and uprooted in a bizarre butterfly-shaped pattern, every tree pointing away from the blast zone like spokes on a wheel. So what was it? The leading theory suggests an asteroid or comet fragment exploded in midair, vaporizing before it could hit the ground. But here's the twist: no debris was ever found. Not a single fragment of rock or ice from the object itself, despite exhaustive searches. This absence has fueled wilder explanations. Could it have been a chunk of antimatter, annihilating itself in a flash of energy? Or, as one physicist proposed, a microscopic black hole zipping through Earth like a bullet through smoke? Even Nikola Tesla reportedly wondered if his experiments with wireless power transmission might have accidentally triggered the blast. The truth is, we may never know for sure. Tunguska's remoteness meant delayed investigations, and by the time researchers arrived, crucial evidence had vanished. But what makes this more than just a historical curiosity is the warning it carries. If a similar explosion happened today over a major city, millions could perish. NASA now tracks near-Earth objects precisely because of Tunguska's legacy, a reminder that sometimes the universe doesn't need a direct hit to remind us how small we really are. And yet, this event also highlights how much we still don't understand about the chaotic ballet of objects hurtling through our solar system, unseen until it's too late. In 1976, NASA Viking 1 orbiter snapped a photo of the Martian surface that would ignite decades of controversy. A mile-long formation in the Cydonia region that eerily resembled a human face staring up from the rust-colored plains. The image, with its shadowed eyes, nose, and even what looked like a faint mouth, immediately captured the public's imagination. Was this proof of an ancient Martian civilization, a monument carved by some long-lost culture, or just a trick of light and angle, the cosmic equivalent of seeing shapes in the clouds? The debate raged for years, fueled by low-resolution images that left room for interpretation. But when modern orbiters like Mars Global Surveyor and Mars Reconnaissance Orbiter returned to Cydonia with sharper cameras, the face seemed to vanish. High-resolution shots revealed a rugged mesa, its features smoothed by erosion. No symmetrical eyes, no deliberate contours. Scientists called it a textbook case of pareidolia, the human brain's tendency to find familiar patterns in randomness. After all, we see faces everywhere, in tree bark, mountain ridges, even burnt toast. Yet the mystery never fully died. Some researchers pointed to oddities in the newer images: geometric angles in the surrounding terrain, clusters of pyramidal mounds nearby that seemed too orderly for natural erosion. Could the face have been real but weathered beyond recognition over millennia? Or was Cydonia once the site of something truly artificial, now buried under dust and time? Even Carl Sagan, a staunch skeptic of extraterrestrial claims, admitted the original image was uncanny enough to warrant investigation. What makes this more than just a case of cosmic misperception is what it reveals about our relationship with Mars. The face became a cultural phenomenon precisely because Mars has always been a blank canvas for our hopes, fears, and imagination. From H.G. Wells' War of the Worlds to Elon Musk's colonization dreams, the red planet symbolizes the ultimate what if. And while science may have debunked the face, the larger question lingers. If Mars did once host life, even microbial, how would we recognize its traces? The line between geology and archaeology blurs when we're dealing with an alien world. Today, Cydonia stands as a reminder of how easily perception can outpace evidence and how much we still have to learn about our planetary neighbor. Every new rover and orbiter sends back thousands of images, each one a potential puzzle piece in the search for Mars' secrets. And who knows, maybe one day we'll find something truly inexplicable, not a trick of the light, but a whisper from the past that forces us to rethink everything. Until then, the face remains a fascinating footnote in the story of our solar system's greatest enigmas. On a quiet August night in 1977, a radio telescope in Ohio picked up something extraordinary, a burst of noise so powerful, so unusual, that the astronomer reviewing the data circled it in red ink and wrote a single word beside it: "Wow." For 72 seconds, this signal blared from the constellation Sagittarius at a frequency scientists had long theorized might be used by extraterrestrial civilizations. Then, just as suddenly as it appeared, it vanished, never to be heard again. To this day, the WOW signal remains one of the most tantalizing and frustrating mysteries in the search for cosmic intelligence. What made this signal so special? First, its intensity, 30 times stronger than the background noise of space, suggested an origin far beyond natural cosmic static. Second, it hit exactly 1420 MHz, a quiet frequency where hydrogen, the most common element in the universe, emits no interference. Scientists had previously proposed this as an ideal cosmic hello channel. And third, its narrow bandwidth matched what an artificial transmitter might produce, unlike the broad frequencies of natural phenomena like pulsars or quasars. Despite decades of searching, no explanation fully fits. Some argue it could have been a comet's hydrogen cloud reflecting sunlight, but the two comets in the area at the time weren't close enough to the right spot. Others suggest a military satellite or Earth-bound interference, yet no known human technology matched the signal's unique profile, the most chilling possibility. That we briefly intercepted a genuine alien transmission, one that either wasn't meant for us or was never repeated. The WOW signal's legacy endures because it's a reminder of both how vast the universe is and how little we've searched. Imagine tuning a radio dial across all Earth's oceans and only checking a single teaspoon of water. That's roughly the scale of our efforts so far. Projects like SETI continue scanning the skies, but space is big and signals fade. Whether the WOW signal was a cosmic fluke or a deliberate message may remain unknown, but it keeps alive the thrilling question: if we heard just once, what else might be out there waiting to be discovered? Venus looks peaceful from afar, a brilliant jewel in the twilight sky, but beneath its shimmering clouds lies one of the solar system's most baffling weather systems. While the planet itself rotates agonizingly slow, taking 243 Earth days to complete a single spin, its thick atmosphere races around the planet 60 times faster, whipping around Venus in just 4 days. This extreme disconnect, known as superrotation, turns everything we know about planetary weather upside down. Picture a colossal hurricane spanning an entire world, with winds howling at 360 kilometers per hour faster than a Category 5 storm on Earth, yet somehow maintaining this frenzy for centuries without slowing down. So what's driving this atmospheric rebellion? The leading theory points to Venus's hellish surface conditions. Temperatures hot enough to melt lead, around 460 degrees Celsius, create unimaginable heat differences between the planet's day and night sides. This thermal contrast, combined with the upward push of solar energy absorbed by those reflective sulfuric acid clouds, could act like a giant engine shoving the atmosphere forward. But here's the catch: computer simulations can't fully replicate the phenomenon. Even when scientists account for Venus's slow rotation and intense heat, their models show the winds should peter out long before reaching such dizzying speeds. Another puzzle: the planet's mysterious gravity waves. These aren't the cosmic ripples from black holes, but vast, slow-moving bulges in the atmosphere, spotted by Japan's Akatsuki orbiter in 2016. Some researchers think these waves might transfer energy upward, like a cosmic whip cracking to keep the upper atmosphere in motion. Others speculate that tidal forces from the sun's gravity, or even friction between different atmospheric layers could play a role. The real shocker, Earth's atmosphere technically superrotates too, but at a snail's pace compared to Venus. Our jet streams might gain an extra few kilometers per hour due to seasonal heating, but nothing like the sustained fury next door. This makes Venus a laboratory for extreme meteorology, showing us how alien a planet's weather can become when the usual rules don't apply. Every mission that studies Venus, from ESA's Envision to NASA's upcoming Veritas, brings us closer to untangling this atmospheric enigma. And who knows, solving it might rewrite textbooks on how all planetary climates evolve, including our own. High above Saturn's North Pole, a shape so perfect it looks like it was drawn by the hand of some cosmic mathematician, dominates the atmosphere. A six-sided jet stream stretching over 30,000 kilometers wide, with each side longer than Earth's diameter. This isn't some trick of perspective or camera artifact. The Saturn hexagon is a real, persistent storm system that's been churning for at least 4 decades, possibly much longer. Imagine a hurricane with razor-straight edges, rotating like a colossal honeycomb stamped into the clouds, its vertices sharper than any natural weather pattern should allow. What makes this structure even more baffling is how it defies planetary norms. On Earth, storms spiral into familiar curves, shaped by fluid dynamics and the Coriolis effect. Yet Saturn's hexagon remains eerily rigid, maintaining its geometric precision as the winds inside scream at speeds over 320 kilometers per hour. One leading theory suggests the hexagon acts like a standing wave, where atmospheric currents interact with Saturn's rapid rotation. The planet spins so fast it flattens at the poles, creating stable angles in the turbulence. Think of it like water swirling around a drain, but on a planetary scale where the forces balance just right to lock the storm into a six-sided pattern. But here's where the mystery deepens. Laboratory experiments can't fully replicate it. When scientists simulate Saturn's conditions using rotating fluids, they occasionally get polygonal shapes, but never with the hexagon's longevity or stark clarity. Some researchers propose that deep beneath the clouds, Saturn's internal heat generates massive convection currents, which rise and interact with the upper atmosphere like invisible hands shaping the storm. Others wonder if the hexagon is a visible imprint of Saturn's magnetic field, a kind of cosmic fingerprint left by the planet's hidden dynamo, the most haunting question. Why 6 sides? Mathematical models show that under certain conditions, polar vortices could form polygons with anywhere from 4 to 8 sides, yet Saturn's North Pole chose 6 with uncanny consistency. Even more bizarre, the hexagon isn't static. It changes color with Saturn's seasons, shifting from golden hues to deep blue as sunlight waxes and wanes over its 30-year orbit. What's at stake isn't just solving a planetary curiosity, it's about rewriting our understanding of fluid dynamics. If we can crack how Saturn sculpts this perfect shape, it could reveal hidden laws governing how turbulence works, not just on distant worlds, but in Earth's oceans and atmospheres too. Every time a spacecraft like Cassini peers beneath Saturn's clouds, we get new clues and new questions. For now, the hexagon stands as a silent monument to the universe's ability to craft order from chaos, reminding us that even in the wildest corners of the solar system, nature has a geometry all its own. The Moon today is a silent, airless world, its surface bombarded by solar winds and cosmic rays without the protection of a global magnetic field. But lunar rocks tell a different story, one of a dynamic past where our nearest celestial neighbor once generated its own magnetic shield, rivaling Earth's in strength. How could something so small, just 1% of Earth's mass, ever muster the energy for such a feat? This puzzle isn't just about ancient magnetism, it's a key to unlocking the Moon's fiery youth and the cosmic forces that shaped it. Samples brought back by Apollo astronauts contain tiny time capsules, minerals like magnetite, frozen in alignment with magnetic fields that vanished billions of years ago. Analyzing these crystals revealed something shocking. The moon's field was once 50 times stronger than Earth's is today, lasting for over 1 billion years before fading away. For a world without plate tectonics or a churning molten core, this shouldn't be possible. Earth's field comes from its spinning iron outer core, acting like a planetary dynamo. But the moon, its core is too small, its rotation too sluggish, yet the evidence is undeniable. Scientists now chase two leading theories, each wilder than the last. The first involves a cosmic dance with Earth. In the moon's early days, it orbited much closer, and tidal forces from our planet's gravity may have violently stirred its molten interior, generating temporary magnetic currents. Think of it like stirring a cup of coffee with a spoon. The friction creates swirling motion. But here's the catch. Models show this effect would have faded within a few 100 million years, not the billion-plus years the rocks record. The second theory is even more dramatic, a lunar magma ocean. Early in its history, the moon's surface was likely a seething sea of molten rock, hundreds of kilometers deep. As this ocean cooled, heavier minerals sank while lighter ones rose, a process called fractional crystallization. Some researchers argue this slow-motion churning, combined with heat from radioactive elements, could have powered a dynamo effect without requiring Earth's tidal pull. Recent simulations suggest this might explain the field's longevity, but there's a twist. The moon's crust shouldn't have solidified so quickly if this were the case. The implications ripple far beyond lunar geology. If a small, rocky body like the moon could sustain a magnetic field, then exoplanets we've written off as too small might harbor hidden potential for shielding life from deadly radiation. It also forces us to rethink how moons form and evolve. Jupiter's volcanic Io or Saturn's icy Enceladus might have had similar hidden histories. Every new lunar mission, from China's Chang probes to NASA's upcoming Artemis landings, brings fresh clues. Maybe the answer lies in untapped rock samples, or in mapping the moon's ghostly magnetic anomalies, patchy regions where crustal rocks still whisper of that vanished field. Solving this mystery wouldn't just rewrite the moon's biography, it could redefine what's possible for small worlds across the cosmos. At the solar system's edge, where sunlight fades to a twilight glow, astronomers have stumbled upon a cosmic boundary that defies expectations, the Kuiper Cliff. Beyond 50 astronomical units, roughly 7.5 billion kilometers from the Sun, the bustling population of icy Kuiper belt objects suddenly drops off. It's as if someone drew an invisible line in the cosmic sand, beyond which very few objects dare to wander. This abrupt decline isn't just curious, it's statistically implausible. The Kuiper belt should theoretically extend much farther, with icy bodies becoming sparser gradually, not vanishing almost entirely. So what's clearing the outer solar system like a cosmic broom? One compelling explanation points to an unseen giant planet 9. This hypothetical world, estimated to be 5 to 10 times Earth's mass, could orbit hundreds of astronomical units from the Sun, its gravity shepherding distant objects into clustered orbits while flinging others into the void. Computer simulations show such a planet could carve exactly the kind of edge we see at the Kuiper Cliff. But here's the catch: despite years of searching, no telescope has spotted Planet 9 yet. Some researchers argue it might be hiding in observational blind spots, camouflaged by the dense starfields of the Milky Way. Others suggest it could be a primordial black hole, invisibly shaping the solar system's fringe without reflecting a single photon of light. Yet there's another, even wilder possibility. The cliff might be a fossilized imprint of the solar system's violent infancy. During the era of planetary migration, when Jupiter and Saturn's gravitational dance hurled Uranus and Neptune outward, these ice giants could have plowed through the Kuiper belt, scattering most of its material inward or ejecting it entirely. The debris left behind would then bear the scars of that ancient upheaval, like footprints in celestial snow. Recent models suggest Neptune's migration alone might explain the drop-off, but the numbers still don't quite add up. Some objects still orbit beyond the cliff, defying even this explanation. What makes this mystery so urgent is what it reveals about our cosmic backyard. The Kuiper Belt isn't just a collection of frozen leftovers, it's a time capsule preserving the solar system's early architecture. Every odd orbit, every gap and cluster holds clues to the forces that shaped our planetary neighborhood. Missions like New Horizons, which flew past Pluto, and the bizarre snowman-shaped Arakoth show just how diverse these distant worlds are. Yet with each answer comes new questions. If Planet 9 exists, how did it end up so far out? If migration carved the cliff, why does the edge look so sharp? For now, the Kuiper Cliff remains one of the solar system's most tantalizing borders, a frontier where our understanding ends and the unknown begins. Upcoming telescopes like the Vera Rubin Observatory might finally spot Planet 9 or reveal stranger truths. Until then, this icy edge stands as a reminder that even in our own celestial neighborhood, the universe still keeps secrets. Mars should be a dead world, its thin atmosphere constantly bombarded by ultraviolet radiation, its surface scoured by dust storms. Yet something on the red planet keeps breathing. NASA Curiosity rover has detected methane, a gas often tied to living organisms on Earth, spiking unpredictably in Gale Crater. These aren't just faint traces. Some readings show concentrations 10 times higher than background levels, only to vanish days later. It's as if Mars is flickering a cosmic Morse code we can't decipher. The intrigue: methane shouldn't linger long in Mars's atmosphere. Solar radiation and chemical reactions should break it apart within a few hundred years, maybe even decades. So why do we keep catching these sudden bursts? One possibility is biological. Underground microbes like Earth's methanogens could be producing the gas as a byproduct of survival. Imagine tiny organisms huddled in briny pockets beneath the frozen soil, metabolizing hydrogen or carbon dioxide and exhaling methane into the rocks above. But there's a geological counterargument. Certain minerals, like olivine, can react with water and carbon dioxide to produce methane without any life involved. Mars's volcanic past might have left pockets of heat and fluid deep underground, fueling these reactions even today. Then there's the wild card. Methane clathrates ice like cages of frozen gas that could trap ancient methane like time capsules, releasing it sporadically when temperatures shift or rocks fracture. The real head-scratcher is the inconsistency. Orbiting spacecraft like Europe's Trace Gas Orbiter often detect no methane globally, while Curiosity sniffs it right at the surface. This disconnect suggests something is destroying or dispersing the gas almost as fast as it appears, maybe a yet unknown chemical process in the Martian soil, or even winds pushing the methane into localized plumes too narrow for orbiters to spot. Every new detection rewrites the playbook. In 2019, Curiosity measured the highest methane levels ever, 21 parts per billion, only for follow-up tests to show the gas had vanished within 48 hours. If life is the source, it's playing a maddening game of hide and seek. If geology's at work, it's a process we've never seen on Earth. Upcoming missions, like the ESA's Rosalind Franklin rover, will hunt for methane and organic molecules with even finer tools. But for now, Mars's methane remains a riddle wrapped in an enigma, a whisper of something active happening right now beneath our robotic explorers' wheels, daring us to guess whether we're seeing chemistry or biology. And that's what makes this more than just a gas leak on a distant world. It's a clue that Mars, even in its apparent stillness, might still hold secrets with the power to redefine what we consider alive. Jupiter's Great Red Spot has been raging for at least 400 years, a tempest so vast that 3 Earths could fit inside its swirling crimson jaws. When Galileo first turned his telescope toward Jupiter in the 17th century, he noted a persistent dark spot on the giant planet, likely this very storm. Yet today, as we watch it through spacecraft like Juno, the spot is shrinking, its once oval shape narrowing into a tighter circle, its winds shifting color from brick red to pale salmon. The question isn't just why this storm has outlasted every hurricane on Earth combined. It's why, despite all odds, it hasn't collapsed entirely. What keeps a storm alive for centuries? On Earth, hurricanes dissipate within days or weeks once they lose access to warm ocean water, their energy source. But Jupiter has no oceans, no land masses to disrupt the flow. Instead, the Great Red Spot acts like a self-sustaining cosmic engine, fed by competing jet streams that drag ammonia and sulfur compounds upward from deeper layers. These gases react with sunlight to form the storm's signature red hue, while the churning turbulence below, possibly driven by heat rising from Jupiter's core, pumps energy into the system like an everlasting battery. But even that doesn't fully explain its endurance. Atmospheric models predict the spot should have fragmented into smaller eddies long ago, its energy sapped by friction or absorbed by Jupiter's chaotic wind belts. Instead, it's as if the storm has carved out a stable niche in the planet's fluid dynamics, a sweet spot where the forces of rotation, shear, and upwelling balance perfectly. Some researchers compare it to a stone in a river. The water, or in this case, Jupiter's atmosphere, simply flows around it, leaving the vortex intact. Then there's the shrinking. Since the 1800s, the spot has dwindled from 40,000 kilometers wide to barely 15,000 today. Some blame changes in Jupiter's wind patterns, which could be stealing energy from the storm. Others speculate that the spot is sinking, getting pulled deeper into the atmosphere where colder temperatures weaken its structure, the most startling theory. That the storm isn't dying, it's transforming. Recent observations show its winds speeding up even as it contracts, like a spinning ice skater pulling in their arms to rotate faster. The stakes here go beyond Jupiter. If we can unravel how the Great Red Spot resists decay, it could rewrite our understanding of fluid dynamics across the universe, from Neptune's dark vortices to the raging storms on exoplanets light years away. Every close pass by Juno peels back another layer, revealing turbulent tendrils beneath the spot's surface and ghostly blades of gas slicing through its core. Yet the more we learn, the clearer it becomes. This isn't just a storm. It's a cosmic artifact, a window into the hidden physics that govern gas giants, and a reminder that even in the violent chaos of space, some things persist against all odds. Beyond the orbits of Neptune and Pluto, far past the Kuiper Belt's icy debris, lies a realm so distant it defies comprehension, the Oort cloud. This vast spherical shell of frozen objects stretches nearly halfway to the next star, a relic from the solar system's infancy. But here's the puzzle. How did trillions of icy bodies end up scattered so far from the sun, loosely bound by gravity yet never collapsing inward? The answer could rewrite the story of how our cosmic neighborhood took shape. One leading theory suggests these objects didn't form here at all, they were stolen. In the chaos of the early solar system, the giant planet's gravitational tug-of-war may have hurled comets and icy fragments outward like cosmic slingshots. Jupiter, with its overwhelming mass, likely played the role of celestial bouncer, ejecting countless objects into the abyss. Some found equilibrium in the Oort cloud, where the sun's feeble gravity just barely keeps them from drifting into interstellar space. This would explain why many long-period comets, those that take thousands of years to orbit, seem to originate from random angles rather than the flat plane of the solar system. They're the survivors of a violent migration, flung to the edges and only occasionally nudged back toward us by passing stars or galactic tides. But there's a competing idea. What if the Oort cloud's inhabitants formed in situ right where they are today? In this scenario, the cloud is a fossilized remnant of the original protoplanetary disk, a region where gas and dust were too sparse to clump into larger bodies. Instead of being ejected, these icy fragments gently coalesced in the deep freeze of outer space, preserved in a slow-motion dance around the Sun. Proponents point to the cloud's spherical shape as evidence. If the objects had been tossed outward by planetary encounters, their paths might have left telltale asymmetries. The debate isn't just academic. If the Oort cloud is a graveyard of exiled objects, studying its composition could reveal what the early solar system's building blocks looked like before planets scrambled them. But if it's a primordial snapshot, untouched by upheaval, it might hold pristine ices dating back to the Sun's birth, free from the heat and radiation that altered inner solar system materials. Adding to the mystery, we've never directly observed an Oort cloud object. They're too small, too dark, and too far away. Even our most powerful telescopes see only the rare visitors that get knocked inward, becoming comets like Hale-Bopp or C/2014 UN-271, a behemoth currently barreling toward us from the cloud's depths. Each new arrival offers fresh clues, but for every answer, they bring more questions. What's clear is that the Oort cloud is more than a distant curiosity. It's a boundary marker for the Sun's influence, a frozen archive of our origins, and perhaps even a cosmic crossroads where the stories of other stars intersect with our own. As we peer deeper into this twilight zone, we're not just exploring space, we're sifting through the fingerprints of the universe itself. Neptune should be a frozen, inert world, a distant cousin to Uranus, bathed in the same feeble sunlight. Yet when Voyager 2 raced past the ice giant in 1989, it revealed something astonishing. Neptune is hot, not just warm, but radiating 2.6 times more energy than it receives from the Sun, its core churning out heat like a dying ember refusing to fade. Uranus, by contrast, is almost perfectly balanced, releasing barely any excess heat at all. So why is Neptune farther from the Sun and nearly identical in size, burning so brightly? This discrepancy isn't just a planetary oddity. It's a window into the violent birth of our solar system and the hidden engines that still drive these icy giants. The leading theory traces this heat back to Neptune's infancy, when the planet was still coalescing from the primordial disk of gas and dust. As gravity crushed these materials together, the compression would have generated staggering temperatures, potentially thousands of degrees, trapped deep in the planet's core. On Uranus, this heat may have bled away quickly, dissipated by an unusually stable atmosphere or an early cataclysm that stirred its interior, letting energy escape. But Neptune, its core might have cooled more gradually, like a thermos retaining warmth far longer than expected. Some models suggest residual heat from this formation era could still be bubbling up through convection currents, slowly escaping as infrared radiation over billions of years. But there's another, more dynamic possibility. Neptune's weather might be fueling itself. The planet's supersonic winds, the fastest in the solar system, could be converting kinetic energy into heat through friction, like rubbing your hands together on a cold day. These winds aren't just surface deep. They could extend thousands of kilometers downward, churning the atmosphere into a giant heat engine. Uranus, with its bizarre 98-degree tilt and sluggish storms, might lack this internal turbulence, leaving its heat to dissipate into space. The wild card, diamonds, yes, really. Deep inside Neptune's crushing atmosphere, methane molecules break apart under extreme pressure, releasing carbon atoms that may crystallize into diamond rain. As these hypothetical gems sink toward the core, their friction could generate additional heat, a phenomenon we've never observed directly, but might explain why Neptune's energy budget doesn't add up. Every new observation, from ground-based telescopes to future missions like NASA's proposed Trident, peels back another layer of this enigma. Solving it wouldn't just reveal why Neptune glows in the dark, it could rewrite our understanding of how all giant planets evolve, and why some worlds, even in the coldest reaches of space, refuse to go quietly into the night. In the vast emptiness of space, where friction and resistance shouldn't exist, two robotic pioneers began slowing down for no apparent reason. Pioneer 10 and 11, launched in the early 1970s to explore Jupiter and Saturn, became famous for another reason entirely: their mysterious deceleration, an anomaly that defied Newton's laws and left scientists scratching their heads for decades. As these spacecraft raced toward the outer solar system, ground stations noticed something bizarre. Both were losing speed ever so slightly, as if an invisible hand were tugging them backward. The discrepancy was tiny, about 800 thousandths of a centimeter per second squared, but over millions of kilometers, it added up to a deviation that couldn't be ignored. At first, engineers suspected mundane explanations, perhaps fuel leaks or thruster malfunctions, but the math didn't match. The deceleration was too consistent, too uniform across both spacecraft, which were millions of kilometers apart. Attention turned to thermal radiation. Heat radiating unevenly from the probe's nuclear power sources might have acted like a weak reverse thruster, pushing against their direction of travel. When scientists accounted for this effect, most of the anomaly vanished, but not all of it. A stubborn fraction remained, whispering of deeper mysteries. This residual anomaly sparked wilder theories. Could it be evidence of exotic physics, dark matter's gravitational drag, or even a flaw in our understanding of gravity itself? Some researchers proposed modifications to Einstein's general relativity, suggesting gravity behaves differently at extreme distances. Others wondered if the spacecraft were sensing the gravitational pull of unseen objects beyond the Kuiper belt. The most radical idea, that we were glimpsing the influence of higher dimensions where gravity leaks away from our familiar three-dimensional space. The Pioneer anomaly became a cautionary tale about the limits of human knowledge. Even in the seemingly predictable realm of orbital mechanics, the universe had surprises in store. It wasn't until 2012, after meticulous analysis of decades-old telemetry data, that the case was mostly closed. Scientists realized they'd underestimated the heat radiating from the probe's electrical systems, which, when combined with the radioactive decay of their power sources, finally explained the drift. Yet the episode left an indelible mark on physics, proving how easily overlooked details can mimic the appearance of revolutionary discoveries. What lingers isn't just the mystery of the pioneers, but the reminder that space exploration is riddled with such ambiguities. Every mission carries instruments calibrated to human assumptions, and when those assumptions collide with reality, the results can rewrite textbooks. The next anomaly might not be so easily explained. It could be the thread that unravels our understanding of the cosmos, hiding in plain sight until some curious mind dares to tug at it. From the depths of space, NASA's Dawn spacecraft beamed back images of something no one expected: a cluster of dazzling white spots scattered across the floor of Ceres' Kuiper crater, gleaming like cosmic headlights against the dwarf planet's shadowy gray surface. These weren't tricks of the light or camera artifacts. They were real, blindingly bright deposits reflecting sunlight with eerie intensity. The discovery sent scientists scrambling for answers. On an airless, seemingly inactive world like Ceres, a relic from the solar system's dawn, what could possibly be creating these brilliant beacons? The answer, it turns out, lies beneath the surface. Spectral analysis revealed the spots as vast patches of sodium carbonate, a salty mineral commonly found in Earth's hydrothermal vents. But here's the twist: sodium carbonate shouldn't just exist in such purity on Ceres' frigid surface. On Earth, it forms when hot water interacts with certain rocks, then crystallizes as the solution evaporates. That raised a tantalizing possibility. What if Ceres wasn't the dead rock we thought it was? What if, even now, briny water was welling up from deep below, carrying dissolved salts to the surface before freezing in the vacuum of space? The evidence keeps mounting. Kuiper crater itself is young by geological standards, just 20 million years old, and its central dome, a messy pile of fractured terrain, bears the scars of recent activity. Some researchers believe this dome formed when a subsurface reservoir of salty water, heated by residual warmth from Ceres' formation or radioactive decay, erupted in a slow-motion cryovolcanic event. Unlike the fiery lava of Earth's volcanoes, this would have been a frigid slurry of water, salts, and mud oozing upward before freezing into the gleaming deposits we see today. Even now, infrared scans suggest traces of water molecules clinging to the salt, hinting that the process might still be ongoing, but Ceres isn't alone in this behavior. Saturn's moon Enceladus and Jupiter's Europa both spew water from subsurface oceans, but they're yanked and heated by their massive parent planet's gravity. Ceres, floating solo in the asteroid belt, shouldn't have the energy for such theatrics. Yet Dawn's gravity measurements revealed a possible underground brine reservoir, a global layer of salty slush kept liquid by antifreeze compounds like ammonia. If confirmed, this would make Ceres the smallest known world with active brine geology, a pocket-sized laboratory for how water and chemistry interact in the cosmos. The implications ripple far beyond one dwarf planet. If Ceres can stay geologically lively without tidal heating, then countless other small icy bodies, from Kuiper belt objects to free-floating interstellar nomads, might hide similar secrets. And where there's brine, there's potential for the chemical building blocks of life. Sodium carbonate isn't just a curiosity. It's a key ingredient in probiotic chemistry, the kind that could have sparked life in Earth's own ancient oceans. For now, Arcata's bright spots remain both a beacon and a riddle, proof that even in the asteroid belt's silent expanse, worlds we dismissed as fossils might still be whispering with activity. Every new mission proposal, from sample returns to advanced orbiters, brings us closer to hearing that whisper clearly. And who knows, the next time we look, those gleaming salts might just tell us something revolutionary about how life finds a way, even in the unlikeliest corners of the solar system. Most planets in our solar system spin like tops, their axes tilted just a few degrees, except Uranus, which rolls around the sun like a drunken giant, tipped a staggering 98 degrees onto its side. This isn't just a slight lean, it's a full-bore cosmic pratfall, with the planet's poles pointing almost directly at the sun during solstices. Even stranger, Uranus's moons and rings share this extreme tilt, orbiting like cars on a sideways Ferris wheel. Something monumental had to knock this ice giant off kilter. But what kind of collision could flip an entire planet and drag its entire entourage along for the ride? The leading theory points to a cataclysm so violent it defies imagination, a collision with an Earth-sized protoplanet in the chaotic early days of the solar system. Computer simulations show that a single gargantuan impact striking Uranus at a precise angle could have delivered enough torque to topple the planet's axis while leaving its interior mostly intact. Think of it like a cosmic pool shot. The impactor wouldn't have shattered Uranus but instead shoved it, sending the planet into a slow, perpetual roll. The debris from this crash might have even formed the planet's irregular moons, explaining why they're locked into the same tilted dance. But here's where things get weird. For an impact to tilt Uranus this dramatically, the smash-up would have needed near-perfect conditions, a glancing blow with just the right amount of force. Too hard and Uranus might have been obliterated, too soft and its gravity would have simply absorbed the intruder. Some scientists argue a single strike is too statistically improbable, proposing instead a series of smaller impacts that gradually nudge the planet sideways. Yet even that raises questions. Why wouldn't those repeated blows have scattered Uranus's moons into disarray rather than leaving them neatly aligned? The plot thickens when you consider Uranus's magnetic field. Unlike Earth's relatively tidy north-south magnetism, Uranus's field is crooked, offset by 60 degrees from its already tilted axis, as if the planet's internal dynamo got scrambled in the disaster. This suggests the impact didn't just rearrange the surface, it may have disrupted the very currents of molten material swirling inside the planet, leaving its magnetic field permanently lopsided. Then there's the question of timing. If the collision happened early in Uranus's formation, why didn't tidal forces from the Sun gradually correct its tilt over billions of years? One possibility is that the impact occurred after the planet had already migrated outward to its current orbit, where the Sun's gravitational influence was too weak to straighten it out. Alternatively, Uranus might have once had a massive moon whose gravity stabilized the tilt, a moon that vanished long ago, torn away by some later catastrophe. Every new clue deepens the mystery. Voyager 2's fleeting flyby in 1986 revealed a world with bizarre weather, storms that flicker on and off despite minimal sunlight, and an eerily uniform temperature, as if the impact siphoned away its internal heat. Upcoming missions like NASA proposed Uranus orbiter and probe could finally untangle whether this tilted giant is a cautionary tale of cosmic violence or a sign that our solar system's past was even wilder than we dare imagine. One thing's certain, Uranus didn't choose this bizarre posture. Something made it this way, and whatever that was, it reshaped not just a planet, but our understanding of how planetary systems evolve. At the very edge of the observable universe, something impossible is happening. Entire clusters of galaxies are moving together in a way physics says they shouldn't. This isn't just random drift. Astronomers call it the dark flow, a mysterious current pulling thousands of massive galaxy clusters in the same direction at breakneck speeds, over 600 kilometers per second, toward a point near the constellations Centaurus and Hydra. The bizarre part, there's nothing there. No supercluster, no cosmic attractor, not even a hint of visible mass powerful enough to tug these galaxies like puppets on strings. This motion defies everything we know about the universe's structure. If gravity is the only force acting across such vast distances, what unseen hand is herding these galaxies like celestial sheep? The implications are staggering. Normal matter, stars, gas, black holes can't explain this. Even dark matter, that invisible scaffold shaping the cosmos, shouldn't create such a lopsided pull on this scale. One radical theory suggests the dark flow might be evidence of something beyond our observable universe, perhaps another bubble of space-time from the inflationary period after the Big Bang, drifting close enough to exert gravitational influence on our corner of existence. Imagine two soap bubbles floating in a bathtub, barely touching. The unseen mass of the neighboring bubble could be tugging at our galaxies through that thin point of contact. But skeptics argue it could be a measurement error. Tracking galaxy clusters across billions of light-years is phenomenally tricky, relying on subtle distortions in the cosmic microwave background, the afterglow of the Big Bang itself. Heat patterns in this primordial radiation suggest galaxy clusters are dragging space-time along with them, leaving wakes like boats churning through water. Yet some researchers contend these patterns might stem from instrument noise or unaccounted for local effects. The debate rages because the stakes are cosmic. If real, the dark flow suggests our universe is far larger and stranger than we dreamed, with entire domains of mass lurking beyond our cosmic horizon. What's most haunting is the timescale. If these clusters are indeed caught in some invisible current, whatever's pulling them must be incomprehensibly vast, perhaps structure on scales so massive it makes our superclusters look like grains of sand. That would rewrite the rules of how matter organizes itself after the Big Bang. For now, the dark flow remains one of cosmology's boldest mysteries, a whisper that the universe we see might just be a backwater eddy in a river whose source we can't even glimpse. 4 billion years ago, our young sun was a dimmer, cooler version of itself, only about 70% as bright as it is today. By all rights, Earth should have been an ice ball, its oceans frozen solid under that feeble starlight. Yet the geological record tells a different story entirely. Ancient rocks from that era show clear evidence of liquid water, even thriving microbial life. This glaring contradiction is known as the faint young sun paradox, and solving it could rewrite our understanding of how planets become habitable. one leading explanation points to Earth's early atmosphere as a planetary winter coat. Today, we worry about greenhouse gases trapping too much heat, but back then, they might have been Earth's salvation. Carbon dioxide levels could have been hundreds of times higher than modern concentrations, creating a dense atmospheric blanket that kept the planet warm despite the sun's weakness. Methane, another potent greenhouse gas, might have added to the effect, released by volcanic activity or early microbes. Together, these gases could have turned Earth into a steamy greenhouse, compensating for the lack of solar energy. But here's where it gets thorny. Recent climate models suggest CO2 alone might not have been enough to prevent freezing. Some researchers propose an even more exotic cocktail of gases, including hydrogen sulfide or ammonia, both incredibly effective at trapping heat. The catch: these compounds break down quickly in sunlight, meaning something must have been replenishing them constantly. Perhaps relentless volcanic outgassing or chemical reactions in a primordial ocean vastly different from today's. Another twist comes from Earth's reflectivity or albedo. With fewer clouds and less land surface in the Archean era, our planet might have absorbed more sunlight than we assume, even from a fainter star. Oceans darker than continents would have soaked up precious warmth, while the lack of ice caps which reflect sunlight could have prevented a runaway cooling effect. It's a delicate balancing act. Too much CO2 and Earth becomes a scorching Venus, too little and it freezes over. Somehow our planet found the perfect middle ground. Then there's the wild card: orbital mechanics. Earth's rotation and tilt weren't always as stable as they are now. A faster spin or different axial tilt could have distributed heat more efficiently, preventing ice from accumulating even under a weak sun. Some simulations suggest a shorter day length, as little as 14 hours, might have reduced temperature swings between day and night, maintaining milder global conditions. What makes this paradox so pivotal isn't just about explaining Earth's past. It's a template for spotting habitable worlds beyond our solar system. If a planet like early Earth could stay warm under a dim star, then countless Goldilocks zone estimates for exoplanets might need recalibrating. Life, it seems, can cling to survival in ways we're only beginning to grasp, and that realization turns every faint, distant sun into a beacon of possibility. The moon wears its asymmetry like a cosmic badge. Turn a telescope toward it, and you'll see smooth, dark plains dominating the near side facing Earth, while the far side bristles with jagged highlands and craters. But the real shock came when orbiters like a Grail mission mapped its gravity. The far side's crust is thicker, stretching up to 20 kilometers deeper than the near sides. This isn't just a superficial difference, it's a fundamental imbalance baked into the moon's very structure, hinting at an ancient tug of war between Earth's gravity and the chaos of the early solar system. Why would a world so small develop such a lopsided shell? The leading theory takes us back 4.5 billion years to the moon's violent birth. Most scientists agree our satellite formed when a Mars-sized object, dubbed Theia, smashed into the young Earth, vaporizing rock and flinging debris into orbit. That debris eventually coalesced into the moon, but it didn't cool evenly. Earth, still glowing from the impact, would have roasted the near side with relentless infrared radiation, while the far side radiated heat freely into space. This temperature difference could have caused minerals to crystallize faster on the far side, creating a thicker crust from the outset. But heat alone doesn't explain everything. Enter Earth's gravity, which was much stronger in the moon's early days. The newborn moon orbited 10 times closer than it does today, and tidal forces would have stretched its molten mantle like taffy. This gravitational kneading might have concentrated denser, heavier minerals like ilmenite on the near side, where they sank deeper, leaving the far side lighter and thicker. Simulations show this process could have created a feedback loop. As the near side's crust thinned, volcanic eruptions flooded the lowlands with lava, forming the dark seas we see today, while the far side stayed high, dry, and heavily cratered. Then there's the wild card, a second moon. Some models suggest Earth briefly hosted a smaller companion moon, formed from the same collision debris. If this mini-moon eventually spiraled inward and collided with our moon's far side, the impact could have dumped extra material there, thickening its crust like frosting on a cake. The remnants of this catastrophe might even explain strange gravitational anomalies, like the sprawling South Pole Aitken Basin, a crater so deep it exposes the moon's mantle. What makes this more than a lunar curiosity is what it reveals about planetary formation. If a world as small as the moon can develop such stark hemispheric differences, then exoplanets orbiting close to their stars might exhibit even wilder asymmetries, perhaps with one side perpetually molten and the other eternally frozen. Every mission, from China's Chang probes to future Artemis landings, peels back another layer of this story. And as we dig deeper, we're not just uncovering the moon's secrets, we're reading the opening chapters of Earth's own violent autobiography, written in the scars of its closest companion. Pluto's heart isn't just a sentimental feature. It's a dynamic engine reshaping the dwarf planet's surface in ways no one saw coming. When New Horizons zipped past in 2015, it revealed Sputnik Planitia, a sprawling basin of frozen nitrogen spanning 1,000 kilometers across, so perfectly shaped it looked sculpted by cosmic hands. But this isn't some static ice cap. It's a living glacier pulsing with movement that carves valleys, spawns mountains, and even generates winds across a world where the air is thinner than a laboratory vacuum. At first glance, Pluto's heart seems frozen in time after all. Surface temperatures hover around -230 degrees Celsius, yet Sputnik's nitrogen ice behaves more like a slow-motion ocean. During Pluto's long, elliptical summers, when sunlight weakly kisses the surface, the nitrogen sublimates, transforming directly from solid to gas. This creates localized pressure zones, stirring winds that blow at just a few kilometers per hour, barely a whisper by Earth standards. But in an atmosphere 10,000 times thinner than ours, these breezes carry bizarre consequences. They transport fine particles of methane frost, sculpting the surrounding plains into patterns that resemble dragon scales or fingerprints, an eerie testament to the interplay between ice and wind. The real magic happens beneath the ice. Sputnik Planitia sits in a colossal impact basin, likely formed by a cataclysmic collision billions of years ago. The glacier's sheer weight, possibly several kilometers thick, has caused Pluto's crust to sag, creating a gravitational anomaly that may have literally reoriented the entire dwarf planet over time. Some researchers think this basin's mass forced Pluto to roll over, shifting Sputnik to its current position near the equator. It's as if the tail wagged the dog, with a single glacier dictating the global alignment of a world. Then there's the convection. New Horizons spotted polygonal cells on Sputnik's surface, each spanning tens of kilometers, evidence that heat from Pluto's radioactive core slowly bubbles upward, causing the nitrogen ice to churn like a pot of thick soup. Warm ice rises in the center of these cells, spreads outward, then sinks at the edges, carrying surface debris with it. Over millennia, this process renews the glacier's face, erasing craters and leaving behind a youthful, unblemished plain. What makes this discovery so revolutionary is what it says about the liveliness of small worlds. Pluto was supposed to be a frozen relic, its geology long since dead. Instead, it's a testament to how even in the Kuiper Belt's deep freeze, exotic ices and subtle forces conspire to keep landscapes evolving. Every revelation, from floating ice mountains to potential subsurface liquid water, paints Pluto not as a footnote in planetary science, but as a masterclass in how the universe surprises us. Mercury should gleam like a polished coin, closer to the sun than any other planet, bathed in relentless solar radiation. Yet when spacecraft like Messenger mapped its surface, they found a world darker than our moon, reflecting barely 12% of the sunlight that hits it. This low albedo, the scientific term for reflectivity, defies expectations for a rocky, airless body. What's painting Mercury in such deep shadows? The answer might rewrite our understanding of planetary formation and the chaotic early days of the solar system. One leading theory points to an invisible artist, carbon. Mercury's surface could be dusted with a layer of graphite, the same material in pencil lead left over from the planet's primordial past. Early in its history, Mercury's magma ocean might have cooled so rapidly that minerals like olivine and pyroxene crystallized first, sinking toward the core. Meanwhile, lighter carbon compounds could have floated upward, forming a thin, dark crust. Over billions of years, constant meteorite bombardment would have ground this carbon into fine dust, spreading it across the landscape like cosmic charcoal. Supporting this idea, messenger spectrometers detected higher carbon concentrations than on any other terrestrial planet, clues that Mercury might once have worn a graphite skin, now buried under later volcanic deposits. But there's a competing explanation. Mercury's darkness might come from vaporized rock. With daytime temperatures soaring to 430 degrees Celsius, certain minerals on the surface could literally boil away under the sun's fury. Compounds like sodium and sulfur would sublimate directly from solid to gas, leaving behind a porous, sponge-like residue riddled with microscopic voids. Sunlight hitting this pitted terrain would scatter unpredictably, trapping photons instead of reflecting them. Think of it like the difference between a smooth mirror and a pile of crushed charcoal. One bounces light cleanly, the other absorbs it. This process, called space weathering, happens on the Moon too, but Mercury's extreme heat accelerates it to an unprecedented degree. The mystery deepens when you consider Mercury's hollows, odd, bright-edged depressions found across its surface. These features, some as wide as a kilometer, appear fresh and uncratered, suggesting ongoing geological activity. One hypothesis posits that volatile materials underground heat up and escape as gas, causing the ground to collapse. If these outgassing events are exposing darker subsurface layers while simultaneously creating reflective edges, they could be contributing to Mercury's patchy, low albedo appearance. What's at stake isn't just solving a planetary puzzler. It's about decoding the recipe for rocky worlds. If carbon proves to be the culprit, Mercury becomes a time capsule preserving conditions from the solar system's infancy, when carbon-rich dust swirled closer to the sun. If vaporization dominates, it showcases how stellar proximity can fundamentally alter a planet's face. Future missions like the joint ESA/JAXA BP Colombo probe now orbiting Mercury aim to measure surface composition with unprecedented precision. Every new dataset peels back another layer of this enigmatic world, revealing that even in the solar system's blistering inner circle, darkness holds its own secrets. After sunset or before dawn, if you're far from city lights, you might spot a faint, ethereal glow stretching upward from the horizon, a slender pyramid of soft light fading into the stars. This isn't twilight or a distant galaxy. It's the zodiacal light, a cosmic phenomenon caused by sunlight reflecting off countless dust particles scattered across the inner solar system. For centuries, this ghostly radiance was thought to be the outer edge of Earth's atmosphere, until astronomers realized its true source, a vast lens-shaped cloud of interplanetary debris stretching from the Sun past Mars, made up of fragments from asteroids, comets, and even planets. But here's the mystery. When scientists calculate how much dust should be out there based on known sources, the numbers fall shockingly short. The zodiacal light shines far brighter than their models predict, as if the solar system is hiding a secret reservoir of dust no one's accounted for. So where's the extra grit coming from? One leading suspect is Jupiter's Trojan asteroids, two sprawling swarms of dark, primitive rocks trapped in the giant planet's orbit. These ancient relics, leftovers from planetary formation, constantly collide and grind against each other, producing fresh dust that could spiral inward over time. Another theory points to comets disintegrating as they loop through the inner solar system, particularly those from the Jupiter family, icy wanderers whose orbits the gas giant has perturbed. Each pass near the Sun vaporizes their frozen surfaces, releasing torrents of dust that linger in space. Yet even adding these sources, the math barely nudges the needle. The zodiacal light remains stubbornly overbright, its glow defying our inventories of cosmic litter. Then there's the wild card, Mars. Recent studies suggest the red planet might be sandblasting itself into space. Dust storms on Mars routinely engulf the entire planet, and some researchers argue these tempests could be lofting fine particles high enough to escape the planet's gravity. If true, Mars's global storms might be feeding the zodiacal dust cloud like a cosmic conveyor belt. Supporting this idea, some of the dust grains sampled by NASA's Stardust mission had chemical signatures eerily similar to Martian soil. But the plot thickens when you consider another anomaly. The dust isn't just brighter than expected, it's warmer. Observations from spacecraft like Parker Solar Probe reveal these particles are absorbing and re-radiating sunlight at higher temperatures than their size and composition should allow. One provocative explanation: the dust might be fluffier than we thought, like microscopic snowflakes with intricate structures that trap heat. Alternatively, some grains could be coated with dark, heat-absorbing materials like amorphous carbon, turning them into tiny solar ovens. What makes this more than just a bookkeeping problem is what it reveals about the solar system's hidden activity. The zodiacal light isn't static. It's a dynamic, ever-changing phenomenon shaped by collisions, planetary migrations, and even the solar wind. Future missions like Japan's planned Destiny Plus aim to fly through this dust cloud, analyzing its composition in situ. Every speck holds clues to the solar system's violent past and its ongoing evolution. For now, that soft glow in the night sky remains a luminous reminder. Even in the void between planets, the universe is far from empty. Jupiter's gravity is so powerful, it sculpts the solar system, flinging asteroids into chaotic orbits, shielding Earth from impacts, even shepherding swarms of rocky followers called Trojans. These cosmic hitchhikers cluster at two special points in Jupiter's orbit, known as L4 and L5, where gravitational forces balance perfectly. Here, objects can park indefinitely like cars in a celestial rest stop. Hundreds of Trojans orbit these stable zones, remnants of the solar system's infancy. But here's the catch: they're all trailing Jupiter, occupying only the L5 point. The L4 region, which should be equally stable and crowded, sits eerily empty. It's as if half a parking lot has been mysteriously roped off while the other half overflows, and no one knows why. This lopsided arrangement defies basic orbital mechanics. Both L4 and L5 are so stable, they've been proposed as ideal spots for future space stations, yet nature seems to favor one over the other. Some researchers argue the imbalance might stem from Jupiter's turbulent youth, when the giant planet's migration through the early solar system sent gravitational shockwaves through the asteroid swarms. If Jupiter plowed through a denser patch of debris during its outward journey, collisions or ejections could have cleared out the L4 group while leaving the L5 swarm relatively intact. Think of it like a snowplow shoving flakes to one side of the road, only here, the flakes are mountain-sized chunks of rock. But there's another, more subtle possibility: Saturn's meddling. The ringed planet's gravity tugs on Jupiter's Trojans with a rhythmic pulse, creating a resonance that might have gradually destabilized objects at L4 over billions of years. Computer simulations show this effect could have acted like a cosmic sieve, filtering out vulnerable asteroids while leaving the hardier ones behind at L5. The surviving Trojans might even owe their durability to their composition: darker, carbon-rich bodies that resist fragmentation better than their brittle, silicate counterparts. The most tantalizing clue lies in the Trojans' colors. Recent surveys reveal the L5 swarm contains more reddish asteroids, while any L4 survivors would likely have been bluer, a spectral difference hinting at distinct origins. Perhaps L4 originally held icy objects from the outer solar system, delivered by Jupiter's gravitational heist, while L5's darker rocks are primordial locals. If so, the empty zone might be a graveyard of volatiles, their fragile ices long since vaporized by sunlight or shattered in collisions. What's at stake isn't just a bookkeeping problem for asteroids, it's a window into how planets bully smaller bodies during their formative years. NASA Lucy mission, currently en route to study Jupiter's Trojans, could finally crack the case by comparing the chemistry and orbits of both groups. Until then, the void at L4 stands as a silent challenge to our models, reminding us that even in the most predictable corners of space, nature reserves the right to surprise us. And somewhere in that emptiness, there's a story waiting to be told of chaos, migration, and the delicate dance of gravity that shaped our cosmic neighborhood. The sun's surface blazes at a blistering 5,500 degrees Celsius, hot enough to vaporize diamonds in seconds. But step just a few thousand kilometers above that searing boundary, into the wispy outer atmosphere called the corona, and temperatures suddenly soar to over 1,000,000 degrees. It's as if you walked away from a roaring bonfire and somehow got burned worse the farther you retreated. A cosmic violation of common sense that's left physicists baffled for decades. How can the sun's atmosphere be hundreds of times hotter than the surface below? The answer might rewrite our understanding of stellar physics, and it could hinge on two competing explanations: nanoflares or magnetic waves. First, the nanoflare theory. Imagine the sun's magnetic field as a tangled web of rubber bands, constantly twisting and snapping under the star's churning plasma. Each time these magnetic lines break and reconnect, they release tiny bursts of energy so small they'd be invisible next to a full solar flare, but collectively powerful enough to heat the corona like countless microscopic matches. These nanoflares would erupt across the sun's surface non-stop, a never-ending firework show too faint for telescopes to spot individually, yet whose combined heat could explain the corona's extreme temperatures. Recent observations from NASA's Parker Solar Probe support this idea, detecting faint X-ray flickers consistent with countless minuscule explosions. The catch: even if nanoflares exist, simulations suggest they might not pack enough cumulative punch to account for all the corona's heat. There could be another player in the game. Enter magnetic waves. The sun's interior convulses with turbulent motion, generating ripples that travel upward through its magnetic field like vibrations along a plucked guitar string. As these waves reach the corona, their energy could dissipate as heat. Think of ocean waves crashing onto a beach, their motion transforming into warmth through friction. Certain types of waves, called Alfvén waves, are particularly promising candidates. These aren't your typical light or sound waves. They're oscillations in the magnetic field itself, capable of carrying energy vast distances without losing much power. Instruments like the Solar Dynamics Observatory have spotted these waves racing through the corona at thousands of kilometers per second, their energy potentially dumping into the surrounding plasma like a cosmic microwave oven. But here's where it gets messy. Both theories face glaring gaps. Nanoflares struggle to explain why the corona's heat isn't uniform. Why do some regions, like the feathery streamers visible during eclipses, reach temperatures of 2,000,000 degrees while others stay relatively cool? Waves, meanwhile, have trouble accounting for how energy transfers so efficiently from the sun's interior to its outermost layers without getting lost along the way. Some researchers now suspect the answer isn't one or the other, but both: a delicate interplay where waves transport energy upward, only for nanoflares to release it in a frenzy of tiny detonations. What keeps this mystery alive is its sheer scale. The corona isn't just a scientific curiosity, it's the birthplace of the solar wind, the stream of charged particles that defines the boundaries of our entire solar system. Understanding how it heats up could help predict space weather, shielding satellites and astronauts from deadly radiation storms. Every mission that flies closer to the Sun, from Parker to ESA's upcoming solar orbiter, peels back another layer of this enigma. And as we stare into that million-degree glow during the next total eclipse, we're not just seeing light, we're witnessing one of the universe's greatest unresolved thermodynamics puzzles, written across the sky in plasma and magnetism. The Moon was supposed to be a geological corpse, a frozen relic with a volcanic past that ended billions of years ago as its small core cooled into stillness. But lunar rocks tell a different story. Hidden in the Sea of Tranquility and other dark plains are volcanic deposits so fresh they'd barely count as wrinkles in cosmic terms, some just 100 million years old. That's younger than the reign of dinosaurs on Earth. This discovery shatters the long-held belief that the Moon's internal fires flickered out shortly after its formation, revealing instead a world that stayed volcanically active for nearly 90% of its existence. So how could such a small body, just 1/80th Earth's mass, keep its furnaces burning so long? The secret might lie in radioactive decay. Elements like uranium and thorium, trapped deep in the Moon's mantle during its violent birth, could have acted like natural nuclear reactors. Their slow, steady disintegration producing enough heat to melt rock and fuel sporadic eruptions long after conventional cooling should have starved the Moon's volcanoes. Picture a stone pulled from a campfire. Its surface chills quickly, but the interior stays warm for hours, now scaled at up to planetary proportions with radioactive elements as the embers. But heat alone doesn't explain the timing. Lunar orbiters like NAS, a lunar reconnaissance orbiter, spotted volcanic features called irregular mare patches, odd, blister-like mounds with smooth, uncratered surfaces that scream geological youth. These formations bear no resemblance to the ancient lava floods that carved the Moon's dark seas. Instead, they hint at thick, sticky magma oozing to the surface in gloopy eruptions, more like toothpaste squeezing from a tube than the fiery fountains of the Moon's youth. Some scientists argue this viscosity points to a change in the Moon's plumbing, a shift from deep, mantle-fed eruptions to shallow, crustal squeezes as internal temperatures wane. Here's where it gets truly bizarre. The youngest lava flows cluster near a region called the Procellarum creep terrane, a vast radioactive hotspot enriched in potassium, rare earth elements, and phosphorus, hence creep. This area might have functioned like a lunar pressure cooker, concentrating heat-generating elements in a way that extended volcanic activity by billions of years. Imagine a planet's last gasp of volcanism clinging to one stubbornly warm corner, like a dying campfire with one final ember refusing to fade. The implications ripple far beyond lunar geology. If small, rocky worlds can stay geologically lively through radioactive trickle feeding, then exoplanets we've written off as dead might harbor unexpected activity, underground magma chambers, cryptic geysers, or even the chemical precursors for life in their lingering warmth. Every new lunar sample, from China's Chang missions to future Artemis landings, brings us closer to reading the fine print of the Moon's unexpectedly vibrant autobiography. And one thing's clear, the dead world narrative was dead wrong. Look closely at the asteroid belt between Mars and Jupiter, and you'll notice something strange. It's not a uniform field of debris. Instead, it's pockmarked with eerie, empty zones where asteroids seem to vanish entirely. These aren't random voids, they're called Kirkwood gaps, and they're cosmic ghost towns carved by Jupiter's gravitational hand. The math behind them is as precise as clockwork. Asteroids orbiting at certain distances from the Sun, specifically where their orbital periods sync up perfectly with Jupiter's, get yanked violently out of place, flung into chaotic paths that eject them from the belt entirely. It's a gravitational game of pinball where Jupiter acts as the ultimate bouncer, clearing out entire neighborhoods in a celestial eviction that's been ongoing for billions of years. Take the gap at 2.06 astronomical units, for example. Any asteroid orbiting here completes 3 laps around the Sun in the same time Jupiter takes to finish one, a 3-to-1 resonance. Over time, even the gentlest nudge from the gas giant stacks up like a swinging pendulum, amplifying small orbital wobbles into massive distortions. The result: rocks that once called this region home now hurtle toward the inner solar system as Earth crossing asteroids, or get booted into the icy depths beyond Neptune. These gaps are so predictable, they're practically celestial signposts, testaments to the ruthless efficiency of orbital mechanics. Yet there's a twist. Some asteroids stubbornly do survive in these zones, lingering in resonant orbits like cosmic squatters refusing to leave. How? The answer might lie in their shape. Irregular, rubble-pile asteroids, loose conglomerates of dust and rock held together by weak gravity, absorb and dissipate Jupiter's perturbations differently than solid monoliths. Think of it like a boxer rolling with a punch versus taking it head-on. These porous survivors might wobble wildly in their orbits without breaking apart, riding out Jupiter's gravitational punches just long enough to defy the odds. Others could be recent arrivals flung into these gaps by collisions elsewhere in the belt, not yet feeling the full brunt of resonance. But the real mystery isn't just how these gaps form, it's what they reveal about the solar system's past. The asteroid belt today is a shadow of its former self. Simulations suggest it once contained hundreds of times more mass before Jupiter's gravity scattered most of it. Some of those exiled rocks might have delivered water to Earth, while others could have triggered mass extinctions. The gaps, then, aren't just empty spaces, they're crime scenes, marking where Jupiter's influence reshaped the solar system's architecture. What's even weirder is that not all resonances eject asteroids. Some trap them. The Hilda group, nestled in a 3-to-2 resonance with Jupiter, forms a stable triangle of rocks that dance ahead of and behind the gas giant like obedient moons. Why do these asteroids stay put while others get tossed out? The answer might hinge on the exact angle and timing of their interactions, a celestial sweet spot where gravitational nudges cancel out rather than amplify. It's a reminder that the asteroid belt isn't just chaos, it's a dynamic, evolving system with pockets of order hiding in plain sight. The lingering question: whether Kirkwood gaps could hold clues to exoplanetary systems. If we find belts around other stars with similar voids, they'd be telltale signs of hidden giant planets, their gravity sculpting debris from afar. For now, these gaps remain both a triumph of celestial mechanics and a humbling reminder. Even in the quietest corners of space, the universe never stops moving, and Jupiter's influence is far from finished. Beneath the swirling blue atmospheres of Uranus and Neptune, hidden from view by thousands of kilometers of crushing pressure, lies an ocean unlike anything on Earth, an exotic realm where water doesn't behave like a liquid or a solid, but something stranger. Scientists call it superionic ice, a state of matter so bizarre it defies simple explanation. Picture an ice cube that can conduct electricity like copper, flow like honey, and exist at temperatures hotter than the surface of Venus, all while trapped in planetary mantles larger than Earth itself. This isn't science fiction, it's the reality inside our solar system's ice giants, and understanding it could rewrite the rules of chemistry and planetary science. What makes this possible are the extreme conditions inside these worlds. At depths where pressures exceed 1 million times Earth's atmosphere, the hydrogen and oxygen atoms in water molecules get torn apart. Oxygen crystallizes into a rigid lattice like the scaffolding of a skyscraper, while hydrogen ions break free, becoming a frenzied fluid that zips through the structure like electrons in a wire. The result, a material that's simultaneously solid and liquid, capable of generating magnetic fields and possibly even fueling the intense storms that rage in these planets' atmospheres. Neptune's supersonic winds and Uranus's sluggish weather might both owe their existence to the churning dynamics of these hidden, half-frozen oceans. But here's the puzzle: why do these two planets, often lumped together as ice giants, differ so dramatically? Neptune radiates 2.5 times more heat than it receives from the Sun, its interior still seething with energy. Uranus, by contrast, is oddly quiescent, barely emitting any excess heat at all. One theory traces this split to a cataclysmic impact in Uranus's past, a collision so violent it knocked the planet onto its side and dissipated much of its internal warmth. Neptune, spared such trauma, might have retained more of its primordial heat, allowing its superionic mantle to remain more dynamic. Another possibility lies in composition. Neptune's mantle could be laced with more methane or ammonia, lowering the freezing point of its exotic ocean and keeping it perpetually churning. The wild card, diamond rain. Deep in these mantles, methane molecules shatter under pressure, releasing carbon atoms that may crystallize into diamonds. As these gems sink toward the core, their friction could generate additional heat, a process that might explain Neptune's excess energy. Uranus, with its colder interior, could have a diamond pileup near its core, insulating it like a thermal blanket and trapping heat below. What makes these oceans more than a planetary curiosity is their role as cosmic laboratories. Superionic water might be the most common form of water in the universe, hidden inside countless exoplanets between the size of Earth and Neptune. Future missions like NASA's proposed Uranus orbiter could revolutionize our understanding by measuring these worlds' magnetic fields in detail, a fingerprint of their hidden dynamos. Until then, the ice giants guard their secrets, reminding us that even in our own solar system, the most familiar substances can transform into something wondrous and alien under pressure. Beneath the frozen wasteland of Mars's South Pole, something impossible may be hiding: a network of liquid water lakes buried under more than a kilometer of ice. In 2018, the European Space Agency's Mars Express orbiter made headlines when its radar instrument, MARSIS, detected bright reflections near Ultimi Scopuli, a region of layered deposits. These signals matched what you'd expect from bodies of liquid water on Earth, like Lake Vostok under Antarctica's ice. The discovery sparked electrifying possibilities. Could briny aquifers still flow beneath Mars's barren surface, offering a refuge for microbial life? But as with any cosmic claim, the closer scientists looked, the murkier the picture became. The initial excitement hinged on how radar works. When radio waves hit a boundary between materials like ice and liquid, some bounce back as echoes. The strength and timing of these echoes reveal what lies below. MARSIS detected unusually strong reflections in a 20-kilometer-wide zone, suggesting not just moisture, but a stable interface between ice and liquid. On Earth, such readings only come from subglacial lakes, but Mars isn't Earth. Its average temperature hovers around -60 degrees Celsius, and even at the South Pole's high pressure, pure water would freeze instantly. So how could these lakes stay liquid? The answer might lie in salts. Magnesium, calcium, and sodium perchlorates could act as antifreeze, lowering water's freezing point to -70 degrees or lower, creating a viscous, sludgy brine. Yet skepticism flared almost immediately. When NASA Mars Reconnaissance Orbiter trained its SHARAD radar on the same region using a higher frequency that penetrates ice differently, it found no such bright reflections. One explanation: clays. Certain smectite minerals common on Mars can mimic the radar signature of liquid water when frozen. These layered deposits might be creating false positives, their metallic-rich structures reflecting signals deceptively well. Then there's the heat problem. Even with salts, maintaining liquid water would require a geothermal heat source Mars shouldn't have. No active volcanoes, no tectonic friction. Some researchers suggest the weight of overlying ice could generate just enough pressure melting, but the calculations are razor thin. The plot thickened in 2021 when a team reprocessed the original MARSIS data with improved noise filtering techniques. Instead of a single large lake, they found patchy, uneven reflections more like a mosaic of wet pockets than a stable reservoir. Worse, some bright spots appeared where the ice should be too cold even for brines. Alternative theories emerged, perhaps pockets of carbon dioxide ice compressed into a strange, slushy state, or layers of conductive dust trapped in the ice, scattering radar waves unpredictably. What makes this debate more than academic is what's at stake for astrobiology. If liquid water exists today on Mars, no matter how briny or sporadic, it redefines the planet's potential to host life. Earth's extremophiles thrive in similarly hostile places: deep mine shafts, acidic hot springs, even inside nuclear reactors. But if the lakes turn out to be mirages of geology, Mars may be far deader than we hope. Future missions could settle the argument. A dedicated orbiter with next-gen radar, or even a lander capable of drilling through polar ice, might finally glimpse what's hidden below. Until then, Mars's phantom lakes remain both a beacon of possibility and a cautionary tale, a reminder that in the hunt for cosmic secrets, even the most tantalizing signals demand relentless scrutiny. The universe rarely serves up answers without wrapping them in layers of mystery first. The Sun, our closest star, seems ordinary at first glance, a typical yellow dwarf among billions in the galaxy. But when astronomers compare it to stellar twins, they stumble upon a glaring discrepancy. Our star is missing something. Lithium, the third lightest element in the universe, is surprisingly scarce in the Sun's outer layers, at least 150 times rarer than in similar stars of the same age and composition. This isn't just a minor accounting error, it's a cosmic whodunit that challenges our understanding of how stars evolve. And the answer might be hiding in the Sun's turbulent interior or even the birth of our planetary system. Digging into the mystery reveals just how peculiar this deficit is. Lithium is fragile, destroyed at temperatures above 2.5 million degrees hotter than the Sun's surface but well below the scorching core. In most stars, convection, the churning motion of plasma that carries heat outward, should safeguard lithium in the cooler outer layers, preserving it like a fossil from the star's birth. Yet the Sun has somehow scrubbed its surface nearly clean. One leading theory blames overshooting currents' turbulent eddies that plunge deeper than standard models predict, dredging lithium down into hotter zones where it burns away. Picture a whirlpool dragging leaves into the depths of a lake. If the Sun's convection zones reach just a bit farther than expected, lithium atoms could meet their fiery demise. But there's a competing idea, one that ties the Sun's missing lithium to the very existence of Earth. During the solar system's chaotic infancy, the young Sun might have devoured protoplanetary material, including lithium-rich gas and dust. As planets formed, their gravitational tug could have stirred the Sun's outer layers, mixing lithium into hotter regions where it vanished. This scenario, dubbed the planet signature hypothesis, suggests that stars with planetary systems might systematically destroy lithium while those without preserve it. Supporting this, astronomers have noticed a tantalizing trend. Stars hosting giant planets often show lower lithium levels, as if the act of building worlds leaves a chemical fingerprint on their suns. The plot thickens when you consider the Sun's siblings. Open clusters like the Hyades, groups of stars born from the same cosmic cloud, show wild variations in lithium abundance, even among stars nearly identical in mass and age. Some researchers argue this scatter points to an overlooked factor: magnetic fields. Stars with stronger magnetism might suppress convection, trapping lithium near the surface where it survives. If the Sun experienced an unusually active magnetic youth, it could explain the depletion. Others propose that early stellar encounters, close passes with neighboring stars, might have jostled the Sun's interior, triggering mixing events that burned lithium prematurely. What makes this puzzle more than academic is what it reveals about stellar alchemy. Lithium isn't just a cosmic curiosity. It's a key ingredient in the Big Bang's elemental recipe, and its destruction in stars shapes the chemical evolution of galaxies. If the Sun's deficiency is tied to planet formation, it could help astronomers identify other solar systems by analyzing starlight for similar depletion patterns. Future telescopes, like the European Extremely Large Telescope, might finally settle the debate by measuring lithium in stars with unprecedented precision, tracing how it correlates with planetary systems. For now, the Sun's missing lithium remains a hole in our stellar models, a quiet reminder that even the most familiar star in the sky still guards its secrets. Whether the culprit is turbulent interiors, planetary formation, or something even stranger, solving this riddle won't just illuminate our Sun's past. It could redefine how we read the life stories of stars across the cosmos. For over a century, astronomers have scoured the scorched space inside Mercury's orbit, hunting for a phantom population of asteroids that should, in theory, exist. Dubbed volcanoids after the mythical planet Vulcan, once believed to circle the Sun closer than Mercury, these hypothetical space rocks would occupy a blistering no-man's land where temperatures soar high enough to melt lead. Yet despite exhaustive searches, not a single confirmed volcanoid has ever been found. Their absence isn't just a cosmic oversight, it's a puzzle that challenges our understanding of how the inner solar system formed and evolved. The case for volcanoids seemed solid. The asteroid belt between Mars and Jupiter proves small bodies can survive for eons in stable orbits, so why wouldn't the same apply inside Mercury's path? Mathematical models suggested a narrow window of stability could exist between the Sun's gravitational pull and Mercury's disruptive influence, a sliver of space where asteroids might huddle close to the inferno without falling in. Some researchers even speculated these could be relics of the solar system's birth, pristine, heat-blasted remnants too stubborn to be swallowed by the Sun or ejected entirely. But nature had other plans. Early searches relied on grainy photographic plates exposed during solar eclipses, when the Sun's glare dimmed enough to reveal potential interlopers. Not a trace appeared. Later, high-altitude balloons and spacecraft like NASA stereo probes scoured the zone with modern cameras, covering vast swaths of sky where volcanoids as small as 5 kilometers should have stood out against the blackness. Still nothing. The most promising candidate, spotted in 2002 by a ground-based telescope, turned out to be a glitch, a cosmic false alarm that evaporated under scrutiny. So where did they go? One possibility is that volcanoids never existed at all. The inner solar system may have been too chaotic during its formative years, with collisions and the Sun's tidal forces pulverizing any small bodies before they could stabilize. Another theory points to the Yarkovsky effect, a subtle but relentless force caused by sunlight heating an asteroid's surface. Over millions of years, this thermal recoil could have nudged volcanoids outward into Mercury-crossing orbits, where the planet's gravity either flung them into deep space or sent them spiraling into the Sun. Yet the most tantalizing explanation involves Mercury itself. The planet's eccentric orbit and unusually large iron core suggest it may have suffered a catastrophic impact early in its history, a collision so violent it ejected debris across the inner solar system. Any pre-existing volcanoids would have been caught in the crossfire, either shattered by impacts or cleared out by the reshuffling of gravitational forces. This scenario would make Mercury not just a bystander in the volcanoid mystery, but the architect of their demise. The hunt isn't entirely over. Modern surveys using adaptive optics and space-based telescopes continue to probe the region, searching for faint, fast-moving dots that might have eluded earlier detection. Some scientists hold out hope for tiny volcanoids kilometer-sized or smaller, lurking in the glare, their dark, heat-baked surfaces making them nearly invisible to our instruments. Others speculate that if any exist, they might resemble not typical asteroids but something stranger, sintered masses of metal and rock, forged by eons of solar radiation into bizarre, slag-like forms unlike anything found farther out. What's at stake isn't just a tally of missing space rocks. Volcanoids, had they survived, would offer a unique window into the solar system's most extreme environment, a laboratory for studying how materials behave under relentless heat and radiation. Their absence, meanwhile, hints at hidden chapters in Mercury's violent past and the dynamic processes that shaped the inner planets. Every null result, every empty patch of sky whispers the same question. Was this zone always barren, or are we seeing the aftermath of a forgotten celestial upheaval? Until we find proof or conclusively close the case, the volcanoid hunt remains one of astronomy's most persistent ghost stories. Our solar system isn't adrift in empty space, it's cocooned inside a vast, invisible shield known as the heliosphere, a magnetic bubble blown by the sun's relentless solar wind. This cosmic force field stretches far beyond Pluto, shielding planets from deadly galactic radiation and interstellar dust. But here's the twist: this bubble isn't round. Instead, it's lopsided, warped into a shape resembling a deflated football, with one side dented inward and the other stretched into a long, comet-like tail. Voyager 1 and 2 confirmed this asymmetry when they crossed the heliosphere's boundary, revealing a frontier far stranger than anyone predicted. So what's sculpting this irregular cosmic barrier? The answer lies in the turbulent currents of the interstellar medium, the thin soup of gas, dust, and charged particles that fills the space between stars. Picture the heliosphere as a ship plowing through an invisible ocean. As the sun hurtles through the galaxy at 70,000 kilometers per hour, it collides with a patchy mix of interstellar material, some regions dense and slow-moving, others tenuous and fast. This uneven resistance tilts the heliosphere off kilter, compressing one side while the other streams freely behind. Data from NASA IBEX satellite paints an even wilder picture. The interstellar magnetic field, threading through our galactic neighborhood like invisible wires, presses against the heliosphere with enough force to indent its surface, creating a dented nose and a stretched tail that might extend light years downstream. Yet the mystery deepens when you consider the heliosphere's leaks. Far from being impenetrable, this bubble seeps like a sieve, allowing neutral atoms from interstellar space to slip through. Some, like hydrogen and helium, ride the solar wind inward, while others, like enigmatic interstellar bullets of oxygen and neon, pierce deep into the solar system. These intruders carry chemical signatures of distant star-forming regions, offering clues about the sun's journey through the Milky Way. Meanwhile, the heliosphere's own particles escape too, mixing with interstellar material in a chaotic dance of exchange. What's at stake isn't just a map of our cosmic backyard. The heliosphere's shape affects how much harmful cosmic radiation reaches Earth, fluctuations that could have influenced climate patterns and even the evolution of life. Future missions like NASA Interstellar Probe aim to chart this boundary in 3D, revealing how our star's influence wanes as true interstellar space begins. Until then, the heliosphere remains a reminder. Even in the void, nothing stays still. The solar system breathes, flexes, and adapts to forces we're only beginning to understand, a bubble forever shaped by the unseen hand of the galaxy. From the eerie hexagon swirling over Saturn to the phantom lakes hidden beneath Martian ice, these 30 mysteries prove one thing beyond doubt: our solar system is far stranger, far more dynamic than we ever imagined. Think about it. We've sent probes to every corner of our cosmic neighborhood, mapped planets with pinpoint precision, even landed robots on distant worlds, and yet with every answer we uncover 10 new questions. The moon shouldn't have volcanoes younger than dinosaurs, but it does. Pluto's frozen heart shouldn't pulse with glacial activity, yet it thrives. The sun's corona shouldn't burn hotter than its surface, and yet, defying logic, it does. These aren't just gaps in our knowledge, they're glaring reminders that the universe operates by rules we're still deciphering. What's truly humbling is realizing how much lies beyond our current understanding. Take Jupiter's Great Red Spot. We've watched it rage for centuries without fully grasping its fuel source or why it's suddenly shrinking. Or consider the Oort cloud, that ghostly shell of icy nomads where comets are born. We've never even seen one of its objects directly, only glimpsed the rare visitor it sends our way. Even Earth isn't exempt from cosmic riddles like the faint young sun paradox. How did our planet stay warm enough for life when the sun itself was so much dimmer? These puzzles aren't academic, they're clues to forces that shaped our existence and might determine the fate of other worlds beyond our solar system. And that's the real magic of space exploration. Every unsolved mystery is an invitation, a challenge to future scientists, engineers, and dreamers to push further, dig deeper, and rewrite what we think we know. Maybe you're the one who'll crack the case of Mercury's missing volcanoids, or unravel why Neptune's interior burns hotter than Uranus. Perhaps you'll spot the flaw in our models that explains the Kuiper Cliff's abrupt edge, or finally prove whether Phaeton, that lost fifth rocky planet, ever truly existed. Science isn't about having all the answers, it's about asking better questions, and the solar system is overflowing with them. So tell me, which of these enigmas keeps you up at night? Is it the dark flow, that inexplicable current tugging galaxies beyond our horizon, the wow signal, that haunting whisper from the cosmos we still can't explain? Or maybe it's the face on Mars, that iconic reminder of how easily our minds find patterns in the unknown. Drop your favorite mystery in the comments. I read every single one. And if you're hungry for more cosmic wonders, hit subscribe and ring that notification bell. Because the universe, it's just getting started, and so are we.